Chapter 12, torsion in circular sections, and what more to say? Let's just get started. So it's a twisting action that's caused by a couple or a twisting moment, and it's applied in a plane perpendicular to the longitudinal axis, and that's something that's called torque. Okay, so torque is being applied to this. How come you can't see my mouse, can you? I see it writing. Let's see if you can see my pen. Yeah, okay, you can see that. But the torque is applied here and here. If we're applying it here and here, that's creating a couple, right? Equal and opposite. Okay, so that's known as torque, and that's an external torque that's applied. Now what we're going to be talking about will be internal torque that will resist that. So that's basically what we're trying to figure out. If you've got an external force applied to it, what's it going to take for the material that you're using to resist that external force? Okay, which is nothing any different than what we've been doing up to this point, is it? Worst part about it, I can't hardly see that on my screen. But so we've got some different situations that are occurring here, and you can, if you're following along in the book, maybe that's about my best bet as far as being able to see it. We've got two situations that are occurring here. Okay, you've got, well, in that particular example, basically only shows one, doesn't it? Okay, well, you've got two different situations that are occurring here. You've got, well, let me back up a second. You've got those two states to consider, but you also have to consider that these members are in static equilibrium. In other words, nothing is moving here, right? Which is kind of where we've been the whole semester. But you've got the situations where the subject are subjected to twisting actions caused by either a pair of externally applied couples acting in parallel planes, okay, which you will see in the next slide, which is using pulleys, okay, or a single external couple applied to a member that's fixed on one end, which is what you're seeing in this example. I guess really equal and opposite, they're showing it in this top left example. You are seeing that. Let me get my pen here instead of the highlighter. But they're not showing the actual pulleys. So when you go to the next slide, you'll see this situation is occurring here. This is the two equal and opposite, or the couples. Okay, and then in the top portion here, now what they're showing you here is this free body diagram is where they're cutting through somewhere in this section right here. Oops, somewhere in here they're cutting through, and that's where you're looking at that section. So you're when we consider the torque or the torsion in these mechanisms, if you will, we're going to be looking at some area, if you will, inside the two couples. You can cut it anywhere in between there, and it's going to be pretty much the same no matter where you're at within those two external forces, if you will. There's some kind of torque that's being resisted within those two planes. Okay. Same thing is occurring on this second one here, but the wall is resisting as opposed to a cup, or as opposed to one of the pulleys. So it is actually creating an internal torque in that helps resist it. So something has to hold it back for that thing to have torque, right? If they're internal torque. If it's freely spinning, nothing, if you just, in theory, it would just keep spinning forever, right? There's no torque involved. It's not, there's nothing trying to make that thing twist apart, if you will, if there's no resistance. But as soon as you put resistance, in other words, and they could actually be going in the same direction, but there's something out on the end of that chain, if you will, on that pulley that is having to be driven. You've got a motor driving this whole shaft, and then that shaft transfers energy to another shaft that's turning a wheel, let's say, on your lawnmower. My old lawnmower was like that. It had drive motors, and they had a sprocket on them, and there was a chain down to the wheel. Well, there's still torque applied in that shaft in there, in both of those shafts. But they're still turning in the same direction. But there's resistance from the ground making that tire want to resist, if you will. Okay, between the ground and the gravity, there's resistance there. Now, if all of a sudden I break traction, if I'm in a dragster now, a dragster lawnmower, torque goes away, doesn't it? Shaft, there's nothing to resist that. But as soon as it bites again, torque is back involved. And they were still going the same direction. Both shafts were going the same direction. So don't think that that it can't be moving per se. You can still not have torque. They both are still moving, and they can both be moving in the same direction. But there's still some kind of external force being applied to that system to make it drag down, if you will. Okay? So keep that in mind too. Now, in the case of the wall there, no, sorry, it's not moving. If it's moving, it's deforming, isn't it? So there's always going to be I guess there'll always be some kind of torque there as long as you've got something trying to twist it. If there's nothing trying to twist it, of course, there wouldn't be any.
What did you mean when you said if you went to from your regular mower to a dragster, then?
Well, if you broke traction. I broke traction, and now I'm just smoking the tires right to.
Okay, so there's nothing resisting you there.
Exactly. Yeah. That was just a maybe a fun example, Although I guess even at the drag strip when they pour down their liquid and smoke the tires, there's still resistance in there. If there wasn't, you wouldn't have any smoke. So there is still resistance, so there is some torque still applied. But if you were sitting on ice, it wouldn't be, maybe. Wouldn't be any, would there? That's the worst thing for an old guy. Ice.
Isn't that how?
Break a hip.
Isn't that how like the perpetual moment clock works? Like they're trying to remove all the torque and tension in there.
And friction, yeah. So, which I guess it was Tesla. He was one of the only ones that ever basically came up with that, and then they shut him down. So let's see what else here on that particular slide. It's easier for me to read this one. Yeah, we talked about all that. Now, I think that's the last slide I actually have any real knowledge, if you will, imparted any knowledge there. But let's see. Now, we've got case of two equal externally applied couples acting in opposite directions on parallel planes, and that's basically what we've got going on in this example. Okay, so we've got this shaft. Now, somewhere in there, does it say, yeah, here's the driver pulley. Okay, when you've got a shaft situation, you've got to have a driver pulley. In other words, this one is getting all of the torque supplied to it via some kind of a V-belt, a chain, or it could even be another pulley, couldn't it, in contact with it. I've seen rubber pulleys where they have rubber around the outside, and they just contact each other, and so a motor is probably supplying some kind of an external force to this of 2,400 pounds inches, excuse me. Then you've got these other pulleys. Now they're going in different directions. Okay, so you're going to have some kind of torque buildup in that shaft, aren't you? Let's see, and it is parallel planes. All these pulleys are on parallel planes. What else about that? Let's see. I guess we talked. Well, the magnet. Note that, and let's back up here one. We should still be talking about this. In Figure 12, let's see, 12.2b. What they said, basically what we said there was this bar is cut in half, and you're only looking at one side of it. Okay, and what you can say about that, the magnitude of the torque in that bar is equal to one of the two couples, and that is denoted as the force D. Okay, and do they have that? Did they show that there? Yeah. Over here they say the torque is equal to FB, and it's just the force times the distance of one of those couples. Okay? So the force times the distance of just one of the two couples. So when you cut it in half, you're taking care of that, aren't you? Okay? So I guess what would the other one would, and I think I did allude to this, the other pulley acts like the wall, doesn't it? Because the torque in that bottom shaft is the same thing. It's the force times the distance, or just the moment, right? So, does that make sense? That the torque would be the force times the distance, or the moment? Think about a torque wrench, or any kind of a wrench. What are you developing? You're developing that moment, which is a force times the distance. Okay? A little bit different there, but it's
So that distance is not to the axis, but all the way between the two arms of the force, or the two forces.
right. That's how a couple works, right? It's one of the forces times the distance between those two. So in other words, if that's the steering wheel, remember I think we talked about that way back when. If it's the steering wheel, it's the distance between your hands on that steering wheel, if you will, and then whatever one hand is supplying. But for them to be supplying, they both have to be supplying the same amount, right? But you don't take two times that force; you just take one. So, excuse me. That's how a couple works. One force times the distance between the two. Or you could even look at that as the diameter, especially when we're dealing with pulleys. Think of that D as a diameter. Might be an easy way to remember it. Okay, so let's see what else about that now. Figure 12, that was 12.2b. 12.2c, the bar is rigidly fixed. There's no rotation. The equilibrium exists due to the equal and opposite internal torque. So again, that's at force times the distance. Note, torque is expressed in units of pounds inches or pounds feet. Okay, you might see pounds feet. They don't talk about pounds feet in here, but on my motorcycle, I'm dealing with pounds feet and pounds inches all the time, depending on what size bolt you're trying to tighten up. You know, the smaller machine screws, you're dealing with pounds inches. When you're dealing with an axle bolt, you're dealing with pounds feet. So that's kind of a little bit of what they say in the book is pounds inches, and they make it sound like that's the only thing you're ever going to deal with. That's not the case. But they do say pounds inches, pounds feet, Newton meters, Newton millimeters maybe. I don't know. I guess that would be the case. But they do. It's not foot pounds. Like you always hear, people will talk about foot pounds. It's pounds feet. All right, Howard?
The distance between two forces should be perpendicular, or maybe and distance?
They have to be perpendicular forces, right? So if you've got some force that's not perpendicular, then you're going to have to break it out and figure out how much is applied to that torque. Is that what you're saying?
The distance D is the perpendicular distance between.
That's correct. Perpendicular to the forces, yes. Is that what you mean?
Showing that inclined distance.
Do what?
They are showing in figure inclined distance is not straight. The D is making angle.
That's all because the.
Well, that's just because it's an isometric view. That would be no different than if we looked at the end of that shaft, the end of this shaft right here. If we looked at the end of that, there's your circular shaft, and there's one force going down this way and one force going up this way. And then the diameter is right here. Okay, so that's D, and this is the force, and that's the force. So it's the force times the distance. Does that help?
Yes, a lot.
Okay. I'm sorry, I didn't understand exactly where we were headed on that. That's why you have to keep going with me here. Sometimes I'm not quite clear on that. Okay? So, expressed in pounds, inches, pounds, feet, Newton meters. Okay?
If we were converting pound inches to pound feet, times 12.
Yep.
Divide.
Or it's either divide or let's see if it's let's see if you're doing, you've got, now that is, keep in mind that is pounds times inches, right? That's what that little dot in there, it's pounds inches or pounds feet. If you were going to multiply that by what, you'd have 12 inches in 1 foot, so you'd be dividing it. Bless you. Okay? So, yeah. And you'd still be, then you'd be at pounds, feet. Now, nice thing about it is you get the right torque wrench, it's all done for you, right? Get one that's digital. Takes care of that. It does Newton meters and all that too, a lot of them. So it's kind of handy.
The ones that scale it for you. Using that. The torque wrench.
As far as, what do you mean by scaling it?
When you put it on there, it'll start dialing up, and that's the digital. It'll dial up until where it is, and it'll kick back down to where it needs to go, and then turn on.
I don't guess, I don't know if I'm following you on that one.
You dial up the digital one. Put
Yeah.
It in there. This one, it doesn't, it calculates it all for you. Just put it on there and pull the trigger, and it does the math. All the gears inside.
Oh, on mine, you just push a button to change the units, and then push it to where you want to go to, and
This one that I saw, so the neighbor has it.
that must be a new fandangled one. Yeah, makes a difference.
Like an expensive torque wrench. So you don't actually wrench on it, so you just put it on there and push a button?
I just get rent the whole.
He doesn't have to actually pull?
It's kind of like an impact wrench.
Okay, now I'm with you. Because it's like, wait a minute, I mean, I set mine and you pull it and it'll start showing you the numbers of torque.
Right.
And when it gets to that value, it shakes, it vibrates and sends off a
Yeah,
light.
Think of an impact wrench style.
Yeah, that's, I've never seen one of those. Okay, so what else about this? Let's see. I guess we need to do that example problem there on, oh, and I did talk about the driver pulley, right? On this, we talked about one is a driver, that's what's going to be supplying the external force, and then the other pulleys will help resist that, so you do have an internal torque going on there. Okay? So the driver, I'm trying to find my mouse. This is the driver, and these would be driven, or what the book calls here is, sometimes they say they're power takeoff pulleys, but I think a lot of times you're going to hear that as the driver and the driven pulleys. Okay? That's what I've always heard it referred to. But it is a power takeoff, isn't it? You're taking power away from that shaft and putting it on something else and making it do something, no matter what it might be. So somewhere down the road, this is, you'll be doing a shaft design problem similar to this in machine design. That is, if you're, I'm assuming you guys are all going to take that. I don't know. So, example problem 12.1 now. Let's see. And this is the right picture, I guess, for that. Calculate the internal torque at sections RR and SS for the shaft shown in this picture we've got here, 12.3. The shaft is acted upon by the four torques indicated, assuming negligible bearing friction. In other words, we're not going to account for any friction based on those two bearings that are holding this shaft together, okay? Which there shouldn't be that much friction anyway. So the solution, note that pulley B is the driver. The other pulleys are power takeoff. So the torque of the 2,400 pounds-inches at B is balanced by the three torques of 600, 1,000, and 800 at A, C, and D respectively, which are in the opposite direction. So, in other words, that thing's in equilibrium, right? Because of those, and they're going the opposite direction. So, you know, if you total those up, they equal 2,400. All right? So therefore, the entire system may be thought of being steady-state equilibrium. It's neither gaining nor losing speed. If the system as a whole is in equilibrium, every segment of the system must also be in equilibrium. True. To determine the torque at section RR, cut section RR perpendicular to the longitudinal axis of the shaft, anywhere between pulley A and B. So we're going to take, in theory, we're going to take a saw, right, and cut that. Well, they're showing it right here, aren't they? RR. Anywhere between A and B. So that's what they're doing here. Okay, and consider the left portion of the free body diagram, or the free body is shown in the next little bit here. So we go to that one, and there's the cut. So, for equilibrium, the summation of the torques must equal 0. And they show that in the book as the summation of the torque equals 0. This is the same as saying that the external applied torque must be balanced by the internal resisting torque that is numerically equal but opposite in direction. So what would the torque in that section be? Just based on that. Not a trick question here now.
600?
600. Going the opposite direction. So if it's 600 pounds-inches, right, going, I don't know how we want to say that, counterclockwise if we're looking at it from left to right, then the torque that's going to be in this shaft right here is going to be 600 pounds-inches going the opposite direction. That's all they're saying there. Okay, now, seems easy, right? What we're probably going to be charged with is figuring out what that 600 pounds is, 600 pounds-inches is on that pulley A. That's what we'll end up having to figure out so that we can figure out what that torque is in that, or that torsion that's, you know, going on in the shaft. But probably more importantly is we're going to have to figure out what the stresses are that are involved there so that we can make sure, and it's going to be shear stress in that. Okay, but it's torsional shear. If you twist something hard enough, you can twist it in two, can't you? In fact, well, a bolt that's locked up, you know, that's rusted, you know, you keep twisting, and sooner or later that thing just spins apart. That's torsional shear. Another case of that, what else? What else could we say? Where else does that happen?
A piece of wire.
Yeah, but that's more of a fatigue type thing, I think, going on there. You know, you'd have to, depending on how ductile the wire is, especially, you know, then you start getting into some other material sciences, like holy cow. So, but the bolt is about the best one I can think of right off the top of my head. You know, if if you've got a bolt that's rusted up, a bolt in the nut, and when you start, oh, and you can even do that. Of course, you can do that to anything that's not rusted too, can't you? If you've got some kind of a, well, let's just say if the hinge on my glasses, you know, if you tighten that too tight, it will pop off and you're screwed.
I
So,
don't understand why they make drain plugs for boats out of brass. I snapped like 3 drain plugs on my boat.
well, it probably has something to do with thrust, would be my guess.
Stainless steel, it works.
Yeah,
Rusty, but it's a soft metal.
and that,
Some drunk idiot gets behind the boat and tightens it too tight, and then I gotta go and get it off.
yeah,
And then break.
Problem with steel and aluminum though is your negative battery terminal, so you go into your chassis on your boat, you get corrosion.
yeah, oxidation, or not yeah, it is kind of an oxidizing,
Yeah.
yeah. Any rust is an oxidation process, isn't it? So, yeah, that I don't know that much about it, but
I don't
that's,
either, but it's frustrating.
yeah. But, and even at that though, it's a softer material. Maybe it's easier to deform to
Seal.
seal that up. I don't know, because that really the rubber around there, isn't it?
No,
There's no rubber involved.
brass to brass. Like
Oh, okay.
inlet's brass, and then
Well, I guess that's how it does tighten up too much and
yeah.
shear it off. Oh yeah, and you don't want that to happen at all. Or sheet metal screws. Sometimes you're putting a sheet metal screw in and you're putting it in a thick piece of material that you can't overcome those threads, and the threads don't just pull out. Then you're going to spin that head of that screw off, and you just did a torque type application where you did a torsional shear. Is what's going
But
on.
deck screws in happen a lot too.
Yeah, same thing. So, yep. So that's where we're at on that. Now let's see what else about this. Okay, so we figured out that that's 600 pounds inches. Again, that's what has to resist between pulley A and pulley B there. That's all you have built up in that. Okay. Well, now what happens? Let's see. Using the same approach, calculate the torque in section S. Well, section S was this situation. We went farther down the shaft. So what do you think might have to happen there? You have to do a summation of those torques, don't you? So as we progress at different places on that shaft, we're going to have different torque ratings, aren't we? So what would you think then in your machine design class, what would you do? You'd ask the instructor, what do I do, right? I know how you guys are now. It's just a different world now. What you would do is you would have different diameters on that shaft, wouldn't you? It wouldn't all have to be the same diameter. Now, if you wanted to over-engineer it, I guess it would be. But how we'll make it all one, that kind of sucks, Or maybe you don't have, the pulleys aren't set up like that you're trying to buy. They'll have different diameters, so you have to make sure that the internal diameter on a pulley that you wanted to slide onto a shaft, would still allow you to create a shaft big enough for that.
You need varying speeds.
Do what?
You need different speeds coming off.
As coming off the pulley, well, and typically they are, because the diameter of the pulley is going to have different speeds coming off. So, but down at the axis though, what's the speed
Of the driver of the power takeoff.
of any of them? Down at the axis of that shaft, the speed is 0. Just like the torque is going to be 0. We'll talk about that here in a minute.
Based on the diameter.
And it goes right back to the diameter of the pulley. That's why they have different speeds, and you'd have different torque values, couldn't you, coming off of that? Different F times D, if you will. So that we're getting a little bit ahead right now, though. So note there on page 249, they do talk about the fact that you do have to sum those torques up. So the internal torque is equal to the external torque, and in this case Now, be careful, because you have to do this a little bit differently. It's note that you've got 2,400 inch-pounds going one direction and 600 pounds-inches, excuse me. I slipped right in there, didn't I? Going the opposite direction. So in this case, to sum those up, it would be 2,400 minus the 600. So what we can say then is between B and C, the torque that would be in that shaft would be 1,800 pounds-inches. Going which direction?
Same as the 600.
The same as the 600 that's showing here, right? Yeah. It's kind of hard to say. Clockwise, counterclockwise, it depends on which way you're looking at it, isn't it? If we're looking at it left, looking to the right, the torque in this shaft would have to be going, well, in this direction right here. Okay, where it says shaft, it's got that arrow pointing. That's the direction that the torque would be. The internal torque would have to be going, isn't it? To resist that. Does that make sense? Remember, the torque in the shaft has to resist the torque that's being applied externally. And if that's the case, this 2,400 is beating the 600 all to pieces. So there's 1,800 pounds-inches going this way externally. So internally, it has to go the opposite direction. Okay? Al, you're looking at me like you're not sure about that.
No, I'm thinking if we're looking at what's going on between B and C,
Oh, you're ahead of the game,
what
huh?
does A have to do with that?
What does what now?
Well, the, between B and C, you get the 2,400 and,
Well, what A has to do with that is A is helping that shaft resist that 2,400 pounds-inches. Isn't it?
yeah.
Well, sure it is. It's all one system, right? They're all keyed together, so they're all spinning. Okay? Again,
Yeah, I got confused because on the first section that we looked at, we're only looking at, what's going on in A and B.
Mhm.
And then we're looking at what's going on between B and C, but A is still involved. And I'm thinking like, well, there's other pulleys down on the end that you're not.
and let's go back to way back when we first started our class, and we did those sections of the when we were looking at members to try to figure out what was going on in those trusses, and we did the method of sections, and we cut that truss, and we looked at everything to one side. So what we did was we cut it, in this case, we cut it early on, and then we cut it again, and every time we cut it, we have to add all those forces that are acting on that new system. So we can't just ignore what's going on at A, because it is still something that's going on this, if you will, new little system that we're diagnosing. So you have to apply all the external forces to this system that are shown for the section we're looking at. Okay?
So section SS includes pulleys A and B.
That's correct. And if we were looking at it from the right side, if we cut it at that section, we would be looking at the pulleys C and D then. See, if we went all the way back to here, if instead of looking at the left side, we were looking at the right side, we would be dealing with C and D. The only problem is we don't have the input
Yeah,
force, okay? So that's why they started on that side and went the other. But there again, we didn't have the input force when we looked at just A either, did we? So you could say, if we, when we get done, well, actually I think we are done, but if we, they kind of, the last line / paragraph of that example says a similar approach results in an internal resisting torque of 800 pounds-inches between pulleys C and D, and zero torque between pulley D and the frictionless end of the bearing. So, in other words, if we did just that, if we cut it, let's see, if we cut it here at S and look back this way, what's going on? Well, if we looked at this, we add those two up, we've got 1,800 pounds-inches trying to go, I can't really see that mouse, trying to go this way, right? Trying to do that. So you would have to have 1,800 resisting back that way, right? That's if we're looking at this same section here. We would have to have 1,800. Well, what did we just figure out we had when we looked at it from the other side? 1,800, right? It makes sense then, doesn't it? It adds up. So 0 equals 0, if you will. Well, then if we cut it at section between C and D, right here, and we only looked at this part, we only have 800 then resisting, don't we? So this shaft can be a little bit smaller. From here to here, that shaft can be smaller. We only have 800 pounds-inches resisting, or that we have to resist. Well, if we cut it right here and looked at the shaft to the right, that's where they're saying we would actually have 0 torque there. Does that mean we can get rid of the shaft? No, not really. Because then we'd have to look at the overall system to see what those two ends would have to work on, right? So, same thing on the other end. If we cut this shaft right here, in essence, that would be 0 as well. There's nothing resisting, no external force and no internal force where that bearing's at. So it's just free to spin. So it's kind of a neat, that part of it's really not that hard. You just have to remember that you've got to figure out what the internal force on that shaft is going to be to resist what is being input from the external forces. So once you figure out what the external forces are, then you can say, okay, well then I know what the internal force has to be because it has to keep it in equilibrium.
So the 0, you could use any material for the shaft, basically?
No, I don't think so. Because there's...
Is it actually true that there could be 800 on one side of that pulley D, and then like an inch away it's 0 on the other side of it?
No, and that's kind of what he's saying. Yeah, it's not, in theory, that sounds really good, but no. I mean, in theory, you could just not have anything there, right?
Yeah, so, yeah, I mean, that's what I'm saying, like you could put a string there versus
Yeah.
a piece of steel technically.
No.
No, yeah,
No,
okay.
not going to work.
Yeah.
You would, and what you would typically do is just leave that shaft the same diameter as what you're going to have on the other side of those two pulleys.
Okay.
And that's what you have to have, because you have to be able to get that pulley on there and hold it in. So, yeah, so that wouldn't necessarily fly. Okay? So that's what's going on there. As far as, okay, if I can figure out what kind of forces are acting on those pulleys, then I can go back and figure out what the shaft has to do to overcome that. Well, then you start getting into, well, that's a little bit down the road, I think, as far as that. Yeah, let's see. Actually, there we go. So, okay, so in the section there, 12.3, torsional shear stress. And I thought I had. Okay, so note what my notes say is using figure 12C. So that's this. Let's go back here and get rid of all this gobbledygook here. See if we can erase all that ink on the slide. And I'd really like that to be bigger. So if we were looking at 12.2C, that's the one on the bottom, right? That situation develops pure shear stress. There's no bending or direct tensile or compressive stress on that. By the way, I didn't take any points off on that first problem on the quiz for not putting tension. That force was tension. I didn't even count it at all. So, but it should have been a tensile stress, right? I mean, when you're pulling something, yeah, when you're pulling something, it's in tension. That's all I wanted.
And the instructions say
To say what it was, to declare it. Yeah.
So, extra credit for that, Brian?
No.
I put it on there.
I might go back. I might give you an extra credit for that. Yeah. If you've got it on there, which I pretty much know who did. Put your pen down. Okay. So if we look at that, again, note that that's strictly pure shear stress. There's no tension or there's nothing pulling that shaft or compressing that shaft. It's strictly tension on the torque, if you will, from that perspective. It's pure shear stress. There's no bending or direct tension or compression on that. The internal resistance to the slippage of the material or the deformation is known as torsional shear stress. And note that all materials have a limited shear strength, and so we're going to have to develop a relationship between the torsional shear stress, torque, and the material's physical properties. So if we look at this figure 12.6 here, some things are going to apply here. So it says when an external torque is applied, there's a shift in the plane occurs, and that's what we're showing here, this shift in this plane. So it tweaks that plane a little bit, doesn't it? The plane still exists, and it stays that same size, if you will, and the radius from O to D is the same as the radius from O to D prime. Okay? In other words, that doesn't change. Now, when it fails, it's probably going to change. Okay? But up to that failure point, no change. Fair enough? So we can create some kind of relationship there. So assuming the stresses stay below that proportional limit, that's where I was talking about, when it starts to fail, when it starts to deform, all bets are off. Okay, and the material conforms to the Hooke's law, which is the stress proportional to the strain law. Then the shear stress at a location on the line EF will be equal to half. I use some shorthand here. Equal to half of the shear stress developed on the outer surface. So the shear stress developed in torsionally loaded circular shafts is proportional to the distance from the longitudinal axis of the member. Okay, so in other words, we can predict, so if we go, in fact, I may be a step ahead of myself, but the torsional shear along this line EF here is going to be half of what it is at CD. Okay, so, or if you were looking at that from an end view, in fact, we can go to this, it'd be something like that. So the torsional shear goes down, if you will, the closer you get to the center. Okay, and it's a linear proportional amount there, as shown by that triangular shape. So you can predict that a little bit better, okay, depending on where you're at on that shaft.
So the distance between R is the same as the distance between O and F in the previous?
Let's see. Okay, so the distance, well, that's...
R in that picture is the same as the distance F in the previous slide?
I don't know that we can say that, because that distance R is going to be, they're using that to say that R could be any number. but it's going to be a proportional amount. They're using that in the next, actually in the equation. There's an equation that's going to show that.
Okay.
So basically that R, and then they're going to tie that to an area. It's one of those infinitesimally small areas, you know, that they're going to be able to move that anywhere and predict what the stress is going to be. So that's what they're looking at there. Actually, it would be just half of C in that picture would be what that EF was.
Okay.
So EF in the previous picture was right here as a point,
Yeah.
okay? But it would be showing up as a point in this. This is the end view of that shaft, isn't it? Okay. So that's what they're telling us on that. So it would be half of the shear as half as much as it would be out at point D. And that's what that picture with all the, that's a distributed load, right? If you will, but graduated down. And again, once we get to the center or to the axis of the part, there's no shear stress. There's no torsional shear in that at all. And in fact, it doesn't move either when you get in your mechanisms class. That speed there will be 0. The RPMs on that, 0.
I'm just having a hard time with it because, like, when you go to break a bolt,
Mhm.
the bolt actually does the shear stress that causes the fracture. Is it just breaking along the threads? That basically what's happening? Because when you break a bolt, it's just it's straight across. You don't see any kind of elevation to it unless it's along the thread. I don't understand.
I mean, you can break a shaft anywhere. It doesn't necessarily have to be at the now. In your case of your bolt, it's more than likely it's going to break. But I've sheared bolts off that I haven't actually sheared them at the thread. Yeah, you can do that. Now, there's something else that made that happen. It might have been rusty, or it might have had a nick in it, something like that.
Because
But
I just don't understand how, like, right at the center, there's nothing there, though. It's just, like, theoretically void of...
well, okay. So what was that calculation? Force times distance.
Well, I understand distance is 0, therefore it's 0, but that's not 100% true, is it? Because you can't...
Well,
there's always going to be something there, right?
if you could find 0, in theory, it's true. In reality, maybe not so much. Because you can't, it's just like making something perfect.
Right.
You can't make something perfect. I don't care what anybody says. Other than, I mean, my mom made me, but other than that, you know. Sorry, couldn't resist. So, yeah, if you could...
If you had an air bubble in the casting or something, that would be a point of failure way before season 0 or something. So
Well, but in theory, yeah, right at the center, there's not going to be a movement. But again, you can't really measure right at the center. I mean, how can you get that small? You know, but in theory, yes. But in reality, not so much. You know, it's just, you can't build a machine that will get that minute. I mean, even your electron microscopes and stuff are not that good, no matter what any scientist tells you. There's always going to be an error somewhere in there. So, in theory, yes, 0. In reality, not so much. Okay? What else about that? Let's see, what else here do we need to say on that? So again, I think I said the shear stress developed in the torsionally loaded circular shaft is proportional to the distance from the longitudinal axis of the member, and the stress equals 0 at the axis and varies linearly to a maximum at the outer surface, which is what that picture depicts for you. Okay? Now the torque equation, if you look on page 251, if you're wanting to find torque, you take the torque is equal to the shear stress times J. Well, what's J? That's the polar moment of inertia. And note, you will be able to find that on the back cover of your book. Okay. divided by c, which is the radial distance from the centroidal longitudinal axis to the outer surface, or to wherever you're trying to find that value. So that's where c here, okay, this c right here, you could actually, if you weren't trying to find it out at the outer surface for some reason, you were trying to find it somewhere in between, you just have to adjust that c, wouldn't you? And you should be able to find that torque value, or that, the torque value anywhere within the confines of that radius. Okay, so I need to say any more about that? Just, you're going to have that equation handy, right? If you want to find torque, you're going to hopefully be able to use that equation right there. Now, what else? You'd have to know what the shear stress was, right? So you might have to calculate that first. I think we did something like that in that last quiz. You had to do this before you could do that on a couple of those problems. So keep that in mind. Also note that the shear stress, if you don't know that, but you know the torque, and you know the radius, and you know the polar moment of inertia, you can rearrange that calculation to get the shear stress, can't you? Well, why would that be important? Aren't you given shear ultimate, or in this case, proportional limits for shear and such on the properties back in the back of the book? So we have to make sure, if we know what the torque value is, we have to make sure we pick the right material and maybe even the right size to be able to overcome that torque value to resist that internally. So we have to work with different things, as we go along here. And that's what it said, that, remember, that relationship between the stress, the, what all was it? Go back to my notes now. Develop the relationship between the torsional shear stress, the torque, and the material physical properties. So that's where these calculations are going to pay off for us. To find the max resisting torque, or the allowable torque, we can rearrange that again. And note that is equation, 12.3. So that last equation, to find the shear stress, if you know those others, is 12.2. 12.3, if we want to find the max resisting torque, or the allowable torque, we'll take the allowable shear stress that would be given in the charts, times the polar moment of inertia divided by that radius value. Okay. Note too that the maximum torque this is the maximum torque without exceeding the ultimate shear strength, or allowable shear stress, and that would be the upper limit. In other words, you couldn't put any more on it than that based on what type of material you picked and so on. So that's what you're looking for there. Let's see. Now I've got the next chart I've got here is, let's see, do we need to do example? Nope, I'm sorry, we still got some more here. So note, for design of solid circular shafts, we can use equation 12.3 rewritten. So if you need to find out what the polar moment of inertia is, that's the equation that's at the top of the where did I find that? Well, yeah, that's this just if you're trying to find the diameter, required diameter, they're developing that calculation. If you want to find the required polar moment of inertia, you take the torque times the C value and divide that by the allowable shear stress. Then if you had a solid shaft, note that the C value is the diameter divided by 2, and that's the then you come up with the second equation there for the polar moment of inertia, which is pi times the diameter cubed divided by 32. And then if you set those equal to each other, you have pi times the diameter to the fourth divided by 32 equals the torque times the C value, which was D divided by 2, divided by the allowable shear stress. Well, if you rearrange that, the required diameter is the cube root of 16 times the torque divided by pi times that allowable shear stress. And that will tell you the diameter of the shaft that you need for a particular project. Okay? Now note down there in that table 12.2, there's typical increments that you can buy if you buy the shaft material that you're dealing with. So for a half inch up to 2.5 inches, they're saying you'll be able to buy that in increments of a 1/16 of an inch. When you go to 2 5/8 to 4, then you're not going to get them in 1/16 of an inch. You're going to get them in 1/8 of an inch. So what you would have to do is, if you had calculated, let's say you calculated the diameter at 2.48. Okay, so that's just a little bit under 2.5, right? But it's more than 2.4375, which would be 2 7/16, right? Well, you wouldn't want to buy the 2 7/16 diameter shaft. You'd want to go to the 2.5. So I think that's what's pertinent about that table. You're only going to be able to get it in increments of a 1/16 of an inch. So if it's somewhere between 2 7/16 and 2.5, you need to step up to the 2.5. That's what, or you could have your machinist turn it down to 2.48. Really, you want to do that work? Because then you're probably going to have to order a special pulley to put on it, because the pulleys tend to match the shafts. So not exactly. Actually, the pulley diameter might be 2.48, and then you have to press it on. It wouldn't be quite that big or that small, but you can press those on. Okay. What else there? We're almost out of time. Not quite. Example 2.12 or 12.2. Calculate the allowable torque that can be applied to a circular shaft. The allowable. That's interesting. The allowable shear stress is 83 megapascals. Assume the shaft is solid and has a 150 millimeter diameter. Now we're starting to find out some information. Assume the shaft is, that's for example A. For B, assume the shaft is hollow and has an outside diameter of 150 and an inside of 125. So for the first one, solid shaft, this will be pretty easy. The polar moment of inertia equals pi times the diameter, which was 150 millimeters, raised to the fourth power divided by 2. So the polar moment of inertia is 49.7 times 10 to the 6th millimeters to the fourth. Remember, it's a moment of inertia, right? So we get back into that situation. Now, continuing on, calculate the allowable torque. Well, the allowable torque was the allowable shear stress times the polar moment of inertia divided by C. Well, let's see. Did they give us the allowable? They did give us the allowable shear stress was 83 megapascals. So that's the same thing as 83 newtons per millimeter squared times the polar moment of inertia, which we just calculated, and then the C value, I think they gave us that. It was 75 millimeters was the, well actually that's the radius, isn't it? 150 millimeter, yeah, so C is a radial value. So you just take the diameter divided by 2.
Question. So your answer is 55 times 10 to the 6th Newton meters,
Mm-hmm.
and then they just changed it to kilonewton meters. I thought kilo was 10 to the third. How did it go from 10 to the sixth to kilo?
Because Newton millimeters, not Newton meters.
Oh, yeah, Newton millimeters, sorry, yeah, all right, never mind.
Yeah, they changed both of them on
Yeah,
you
they
there.
changed both of them, yeah.
Yep. Okay. So, and basically all you're doing here is plugging numbers in. You just have to figure out exactly which number you need to plug in and where you need to plug it in. So, I would expect this test to be even better. So for the hollow shaft now, it's a little bit different. Note, and some people did this on the temperature thing. You tried to do like 0.030 over each one of those temperatures, and that wasn't quite right. You couldn't do that. So same thing on this. You don't want to, if you want to find that polar moment of inertia, note that they're taking the outside diameter minus the inside diameter and raising that to the fourth. Actually, they're taking each one of them and raising them to the fourth power.
I'm saying it's kind of like what I did on that homework where I just, on the brass, like I said, that piece of electric had a solid steel core. And then
Yeah, you tried to
around it.
subtract the areas.
Yeah,
Yeah, or subtract the diameters and
yeah.
then do the area, and that, yeah, you can't do that. And the same thing here. Don't do that here either. Okay, so put those numbers in, raise them to the fourth power, subtract the inside from the outside, and then multiply that by pi, and then divide by 32, and you've got the polar moment of inertia. It shows up as 25.7 times 10 to the 6 millimeters to the fourth. Then the allowable torque, again, we're using the same type of thing there, 83 newtons per millimeter squared times the 25.7 times 10 to the 6 millimeters to the fourth, which was the polar moment, and divide that by that 75 millimeters again. And that's the max out at the end, isn't it? That's why you have to use the 75 there. Okay, because it's like, well, wait a minute, why wouldn't I use the inside diameter, and divide that by 2? Well, you're trying to find the max, and the max is out at the outside diameter, isn't it? Make sense? So that's why you use the 75 there. Well, let's see. Example 12.3. Calculate the maximum shear stress developed in a circular steel shaft when subjected to a torque of 95,000 pounds-inches. Assume the shaft is solid with a 4-inch diameter for the first one. Okay, so we got the solid shaft. We look and we find the polar moment of inertia. It's pi times 4 raised to the fourth power divided by 32. So we had 25.1 inches to the fourth. We take that, substitute it in. Now the equation this time is the shear, the torsional shear is equal to the torque times the C value, which is that radial value, right, divided by the polar moment of inertia. So we've got the 95,000 pounds-inches we were given. The C value is 2. Why is that 2? Because the diameter is 4, right? So the C value is the radius. And then we figured out what the polar moment of inertia was. It was 25.1 inches to the fourth. So we punched those numbers in, and we should find out that max shear stress is 7,570 pounds per square inch. So that would be a number we'd have to go back and make sure that we were below what that would be for that material. Let's see, now the second part of that, you've got a hollow shaft, and the outside diameter is 4, the inside diameter is 2. So again, polar moment of inertia, just take that outside number of 4 to the fourth power minus the 2, which is the inner diameter, to the fourth power, multiply that by pi, and then divide the whole thing by 32. Max shear stress is basically, we're doing the same thing here. The only number that changes is the polar moment of inertia, because it's still a 4-inch diameter outside. So that number, nothing really. The only way that number is going to change is if we said, well, the diameter is 3 instead of 4. then your number at the bottom, that 2 would then be 1.5, wouldn't it? Is the only thing there. And let's see, what else does it say there now? Oh, that number ended up being 8,050 psi. Now it does say the shear stress varies linearly from 0 at the longitudinal center of the shaft to 80-50 at the outer surface. Shear stress at the inner surface can then be calculated by the proportion. So in other words, there's the inner surface, they're talking about the ID, aren't they? The inner diameter. That is the inner surface. So it's 8,500 divided by 1/2, because the 2 is half of the 4, isn't it? So there's 4,025 psi max shear stress going on the inside of that pipe. Example 12.4, calculate the required diameter of the solid circular shaft, steel shaft that must resist a torque of 20 kilonewtons per kilonewton meters. The allowable shear stress in the shaft is 83 megapascal. Select the shaft diameter to use. Okay, so note it says the torque is 20 kilonewton meters, and they're changing that to newton meters. 20 times 10 to the third. That's kind of where you were at earlier, Jeff. Yeah. Okay. Then the allowable shear stress, 83 megapascals. They changed that to newtons per meter squared. So they really didn't change anything other than the units essentially there, right? But they want to get them on the same. So the required diameter is a cube root of 16 times the torque. We were given the torque, right? 20 times 10 to the third newton meters. Divided by pi times the allowable shear. Excuse me. The allowable shear stress was 83 times 10 to the 6 newtons per meter squared. You know what, that would be a good thing that you would probably want to punch those numbers into your calculator and make sure you can get that value. It comes out as 0.1071 meters, and then they just change that to millimeters, which is just moving your decimal point 3 places to the right. So 107 millimeters diameter. Now, but then the last part of that said select a shaft diameter to use. See, if you were given that on a test, you would still have to do that, and that would be one I would probably not look the other way on. Okay, so for that shaft, then the next increment up would be a 110 millimeter shaft, and you would want to go up, but you wouldn't want to go down if it was 105. Because you'd screw up your shear, wouldn't you? Wouldn't be meeting that value. Okay, there are a couple more examples there. Well, obviously, we're not going to get to those today. But and I haven't looked over the homework problems to decide what to give you. So what I will do is I will go back to my office, look those up, and post it. So you'll know what you ought to probably look over between now and Friday. Fair enough?